And the next two speakers, please give them a few. One more time, I just want to say that Satoshi flew all the way from Japan just to come here to give this talk, and he's flying back. And for those of you that have ever been on that flight, it's a long, long flight. So thank you again, Satoshi.
Hi, I'm Tony Stentz. I'm the director of Carnegie Mellon's National Robotics Engineering Center. Next slide, please. Okay, the NREC has a long history that includes a connection to disaster response. As an organization, we grew out of the Field Robotics Center on campus. And the first robots that the FRC built were in response to the 3 Mile Island nuclear power plant disaster in 1979. What you're looking at is the remote reconnaissance vehicle on the left, which was deployed to assess the extent of the damage, and the remote work vehicle on the right, which was designed to go in and to perform demolition. Both of these robots were teleoperated robots. Next slide. This is our robot concept. It's Chimp. It's modeled after a monkey. It includes dexterous hands for performing precision tasks. It also includes strong limbs for forceful interaction with the environment. We have adopted a sliding autonomy control model that includes joint level control at the bottom and semi-autonomous task level control at the top. Chimp includes an immersive user interface that provides the remote operator with situational awareness. Next slide. This is the team. It's an all NREC team. We did that for a couple of reasons. One is we felt we had enough expertise in-house in order to pull this off. The second reason was we felt that by co-locating everyone, that would be advantageous given the pretty fast pace of the challenge. I am the lead principal investigator. I am not a humanoids researcher. I'm also not a manipulation researcher. I'm a mobile robots guy. But fortunately, I'm surrounded by a lot of colleagues who have expertise in this particular area. Okay, so in the area of manipulation, we have Drew Bagnell, Max Likachev, and Sid Srinivasa, who do this sort of thing. This is Sid's robot, Her, okay, doing the task of microwaving some food. So this robot is equipped with sensors that enable it to see the food item, plan a path in order to grasp it, pick it up, plan a path that will put it inside of the microwave oven. It can close the door, and even though it's not shown in this particular video, the Herb is also able to push buttons and to operate the microwave. Okay. Also on the team is Drew Bagnell, and Drew is the lead principal investigator for our RMS team. And you're looking at the Andy robot doing the task of changing a tire. So this is a pretty complex task. It involves using sensors to, in fact, identify the tire and then plan grasping strategies for 2 arms in order to get a hold of the tire and slide it off the bolts without snagging it and then placing it down on the table. Let this play out here. Okay. Chimp is a mobile manipulator, so it has lots of degrees of freedom. And Max Likachev does planning for high degree of freedom systems. This is his PR2 robot doing a door opening task. So the robot needs to grab the handle, turn it, pull the door open, which involves motion of both the base and the arm. Then it needs to brace the door, hold it open, while the robot moves through, and then release it and allow the door to close behind the robot. So there's a lot involved here in terms of sensing and planning, grasping, all with both a mobile base and arms on the robot itself. Okay, like I said, Chimp is a high degree of freedom system, has 4 limbs, so we have a fair amount of experience with this kind of mechanism. This is Eric Meyerhofer, who designs a lot of the robots at NREC. This robot here is a mobile robot designed for use in an underground mine. This type of mine has a very low ceiling, and it can include a number of slopes. And so the robot, in order to move about at times, will need to press its wheels against both the floor and the ceiling in order to navigate. And that involves wheels on arms and even an articulated base. Okay, so we are developing an immersive interface for Chimp, and that involves sensors that can sample the environment. And Herman designs most of the sensors for the NREC, and he designed the sensor pad for the LS3 robot. Al Kelly develops the software that takes this data and constructs a colorized 3D model of the environment. And what you're looking at here is this robot is sensing this environment as it drives. It's building a 3-dimensional model, and it's rendering a view of the environment from a position behind and to the right of the robot itself. We're not looking at the robot because the sensor's mounted on it, so we're drawing a model in the scene. And we've actually shown that this particular way of controlling robots is far more effective, and it enables us to go at higher speeds and make fewer mistakes. We have a lot of experience in NREC building complete systems. That's what we do. Here's another DARPA robot, the Crusher vehicle. We also have challenge experience. This is Carnegie Mellon's entry into the Urban Challenge, the BOSS vehicle. And this guy here was the software lead for the challenge, and he is the program manager for our entry into the DARPA robotics challenge. Okay, as an organization, we're committed to fielding a competitive entry in this challenge, and we encourage all of you to track our progress on the web.
Good afternoon, everyone. I have the privilege and the honor to greet all of you. Thank you very much for your attention. My name is Paul O, and I'm joined by my colleagues, just for eyes, Professor Mike Stillman at Georgia Tech, Professor Dimitri Berenson from WPI, Dr. Shlomo Lee from KAIST, as well as Mr. Robert Elliott from When I first heard about the DRC in mid-spring, I was just shaking my head and I go, who's going to do this impossible task? And behold, it was such a compressed timeline. 15 months we have to actually do the first challenge. And I started to dwell upon it. I slept on it. And I said, well, how can I not do this? How can I not do it being an educator? Being a father of 2 daughters, a 9-year-old and 11-year-old, don't want to do anything with them. And have classmates that are similar, and somebody who was also extremely passionate about international collaboration, that I came out of it saying that we have to do this. This morning we heard from the DARPA director saying that DARPA was birthed in response to this strategic surprise. Another extremely strategic surprise, but although much more quiet, was when Honda released their game. And over the decade or so, there has been somewhat of a race. And it's very interesting that DARPA Robotics Challenge is a call to this and really put the best minds at this and to try and tackle it. Next slide, please. So for those of you who know me, know that I'm very, very passionate about international. Less than 3% of American science and engineering students have any sort of education about global design. And with the world is flat, this is extremely alarming. And it so happened that in 2007, National Science Foundation had a program called the Partnership for International Research in Education. And I thought to myself, well, can humanoids be a way of exciting American students to possibly go abroad and maybe learn from the best designers, electromechanical designers of robots? And I was very pleasantly surprised that it was, that there are students that would be willing to go anywhere to be able to work with world-class hardware. And also to leverage America's leadership worldwide in artificial intelligence and information technologies, that we formed this partnership, and we're very pleased to say that we've been able to send dozens of students across, spending 6 months or more working in Korea alongside our collaborators. Another thing that, as a scientist, that I was very concerned about is that humanoid research is extremely eclectic and ad hoc. Many times in the publications and the literatures, it's very hard to validate how the work is done because it's very specialized hardware. And then that was also a proposition to the National Science Foundation that allowed us to acquire 6 more of these humanoids so that we can really start to benchmark results, formulate some practice, and hopefully establish some foundation theory. So going into the DRC, I said, well, I have no choice but to propose and try to move things forward. Our conviction as a team is that really the brains must be developed in concert with the body. In other words, this is much a software challenge as it is a hardware one. Next slide, please. So why Hubo? Well, the obvious thing is that we've worked with this platform since 2007, but moreover, we've been able to go from the lab to the real world. So, for example, we've been able to formulate these very unique tools that help us to execute what's called a closed-loop design process. Everything from concept to the actual prototype. And so these are some examples. If some of you, follow baseball, this was on ESPN when we threw the opening pitch at the Phillies Cubs games a few months ago. You can see the YouTube if you're interested. These are just some kind of specifics about Hubo, but moreover, form and function is top of its class. It's comparable to the Honda Asimo. But moreover, it's very open architecture. And as an academic institutions, working with students, we really want to be able to go under the hood and be able to show how things are, be able to make improvements, be able to get many eyes on it. And we've collectively accumulated over 20 person years doing this U.S.-Korea collaboration. Okay. For size comparison, I would say it's about a 10-year-old American boy. And we thought that it could be suitable for some of the DRC events. Moreover, we have 7 of them. And so this allows us to do what we call parallel development. And I'll explain that a little bit later. I find that with a very compressed timeline for the DRC, many people will be designing, building, and hacking. But because we already have a baseline unit that we're familiar with, our motto for our team is, well, let's program aggressively, develop the software algorithm framework, modify, again, provide that feedback to our design team, and then perfect. Okay? So this is what's called a rapid prototype, testing and evaluation, and a verification validation cycle. Okay? Moreover, we also have an open Hubo software environment that's built on top of OpenRay, which is very well used in the motion planning community. Next slide, please. So if you could play this video, it just shows some of the latest capabilities that would suggest there's some promise of this approach for the DRC. And for those of you who are here with us this morning, you might have seen Boston Dynamics doing their version of push-ups and the Kung Fu Fighter. We thought, well, we kind of try to replicate that. Moreover, you'll see in this slide, again, this was in the latest IEEE plenary when the designer, Dr. Joe, gave a talk. He showed that this had a 2-hour, 2-kilometer drop-dead duration. These are just some of the capabilities of the hand just say conceptually, could it possibly be used to actuate a vehicle's steering wheel or shifter? Okay, again, here's the link if you want to see some more of the videos. Next slide, please. Again, this is notional. This wasn't programmed or anything, but again, the hypothesis of a 10-year-old boy being able to sit in a vehicle like a Bobcat, possibly walk on a slope, climb ladders. So I think most of us can see 10-year-old boys doing these things. So this hopefully kind of was able to visualize what's possible. Next slide. Okay. So this is our team, and this is very important in that we really want to engage the public on this, the open architecture. The fact is that we have 10 universities working on this, but they range from public universities to private ones, to research-intensive ones, to ones that just do undergraduate education. And it's really to try to make them very engaged in this, because for many of these students, robots are definitely going to be part of their future in their everyday activities. And so these are just some of our team leads. Moreover, each team lead is focusing exclusively on a single event. We felt that having 7 of these humanoids, it allows us to have them just focus, for example, on ladder climbing. That's all, for example, Purdue and Indiana University are doing together. Columbia, with expertise in dexterous manipulation, is just focused on the final event, pump replacement. So we felt that this way we can have redundancy and we can do very rapid response. But moreover, collectively, this bumper sticker shows we have over 200 man-years in expertise in humanoids. Next slide. This is what's called a spiral development chart. The numbers around here are the number of elapsed months. But the fact is that we have what's called rapid prototyping, test and evaluation, and verification and validation, with 3 months before challenge to do final integration. This is just some examples. We didn't know what the actual DRC vehicle is. We had an ATV in the lab. Here we just do some motion capture, how humans do this, import it into our OpenTubo software framework, and just do some final measurements. Next slide. Okay, so again, DRC, why are we doing this? Again, it's about validating this idea of training US students in global design practices. It's to validate this idea of doing parallel development, really taking the very best domain experts to attack this problem, and this hypothesis that we have of really coupling the brains and the body. This is the website. I plan to have a blog on this to document the trials and tribulations. Thank you so much. God bless, and blessings to all.
Good afternoon, my name is Brett Kennedy, and I apologize, I'm going to shortchange the excellent teams both at JPL and Stanford that are working on this in favor of talking about robots. So while saving people and people's stuff is the goal of this program using robots, I'm going to flip it around this time. I'm going to sacrifice people for robots. So I'm going to talk a little bit about RoboSimian today. Next slide, please. But before I really get going on the robot itself, I want to talk about first what it is that we're going to want out of this system, and what is the user going to want out of this system. We believe that the very first thing is that we would like to stick to first responders maximum, that slow is smooth and smooth is fast. And what does this really mean in terms of the way the system is going to get used and what the design implications are? We want to allow the system to allow the operator to be deliberative. We believe that's the way that first responders would like to act. They want to be very careful, and they want to be able to plan what they're going to be doing. And the system that allows them to do that should accommodate that operation mode. We'd also like to get this thing out there as fast as we can. So we're picking the things that are going to allow us the earliest field deployments. That means, which is an interesting thing in the research crowd, that we'd like to design within the box. We don't want to have to appeal to anything exotic if we don't have to. And only in very specific cases would we actually look for far-out component technology. We believe that the concept of the robot itself is enough of a reach. Along those lines as well, we're going to pick those solutions that are the lowest cost and that are manufacturable for those things that are custom to the robot itself. And then finally, a huge portion of the design of equipment in the field is what you're going to do with it in the field when it's not operational. So how do you repair it? How do you perform the maintenance? And paying attention to that up front will save us from any architecture breaking issues when we actually try to put this out into the field as a natural, effective unit. The final thing, and the thing that actually lends itself to the RoboSimian name, is that we want to generalize the system elements in order to get the maximum operational flexibility. So this is a very simian attribute. People are lousy simians as far as that goes. So we're looking for a slightly more basal model for our approach. Next slide, please. So, in terms of that physical layout, that simian layout, as you might expect, it's got a body. It's a little tough to get away without it. And it has 4 limbs. So that's your basic simian aspect to it. Something else that it more or less keeps in common with simians is that it has a high degree of freedom limb. And this is the key aspect, is that it is a limb, not a leg or an arm. So we expect that each one of these limbs will be equally effective for mobility and manipulation. Given that, we're going to distribute not only the limbs, but all of the sensory capabilities in planar and axisymmetric manner so that this system is as directionally agnostic or orientation agnostic as we can make it relative to its functions, whether those functions be sensing or mobility or manipulation. Next slide. The hand design, and it's tough because I don't have a good word like limb to describe what we're actually looking for, but it is both hand and foot as necessary. We believe this is the first time that anybody has explicitly designed a manipulator for mobility purposes, like knuckle walking. Not only would you look to modes like knuckle walking, but as you can tell, this is a very philosophically manipulative system, and we would look to those manipulation capabilities to augment the capabilities in mobility. So we want to be able to grasp our terrain if that's an advantage to us. Then for the more strictly manipulation aspects of things, we believe that the 3-fingered layout has been shown to be capable of 9% of all the grasp that a human hand can do, so we will stick to that general layout as the most robust way to get the greatest amount of functionality. Next slide, please. The perception system, we talked a little bit before about the symmetries, but basically it breaks down to 2 different types of stereo camera setups that are arranged about the body. The first is hazard cameras, or HazCams. This is a direct descendant of the types of systems that are on Mars today. There's more of them. And they be arranged about the body so that there is equal mobility perception, both front, back, and to the sides. The second type of system is as the robot moves into more manipulation poses, which we expect to look a bit more bipedal, that we would switch over to these manipulation cameras and have a narrower field of view and better resolution. And they would be concentrated towards those workspaces that we expect the bimanual manipulation to occur. Taken all together, however, this gives us a full hemispherical capability in terms of perception. So immersive GUIs and things of that nature will quite naturally take to this. I think anybody that has used any of various street-view mapping technologies would recognize this kind of outlook on things. Next slide, please. So finally, in summary, we have a few different illustrative poses of the different challenges. As you can see, the system is, in fact, intended to be that very stable tortoise. We expect to make use of quasi-static poses as much as possible. We can always brace ourselves against the terrain or the objects we're manipulating. If you need to use human type of equipment, such as the vehicles, you're capable of taking a very human-like pose within them. But in fact, as many chimps and other apes have shown, sometimes things that aren't human can actually use things that are intended for people even better than people can. So we want to take advantage of that kind of flexibility to learn how to use the system to its best advantage. And with that, thank you very much.
My name is Nicholas Bradford. I'm PI for the NASA Johnson Space Center on the Untitled Robotics Challenge. And next slide. We have a pretty large team, led by NASA, of course, at JSC, Houston, Texas. We've got some universities, University of Texas, Purdue, Texas A&M. I'm just going to jump right into the team. I know there's been a lot of background. I'll get into some background on that a little bit later. But we've got a lot of NASA contractors, Jacobs Engineering on site. We're also partnered with IHMC. We've recently released some exoskeleton work with them, where we're using some of our new actuators. SUNY Buffalo and Lockheed Martin, a lot of advanced materials are coming out of the aerospace community, and we're going to be taking advantage of that. So next slide. So here's how we are architected. Again, NASA is serving as the PI in project management. We've taken kind of a different approach to project organization. We've moved away from functional groups and moved into what we call element groups, which are very multidisciplinary. Having worked in the robotics field now, at least I have for 10 years at NASA, I've seen several instantiations of program and project management for robotic projects, and robotics by nature is very interdisciplinary, and so we're just recognizing that early on and organizing our structure to that effect. So we've got essentially two sides of it. We've got a software architect and a chief hardware engineer. And then we've got production that reports to the chief hardware engineer, and we actually built a new lab and facility at JSC to house this project. And so then we've got these 6 element groups, and I'll get into the specific responsibilities of each of our partners, but essentially, we've divided into mobility manipulation as one group, behaviors and perception, human robotic interfaces, essentially is our software bundle, and then we've got our actuation structures and computer systems and power. NASA's probably going to be pretty tight with at least the JSC side. On our JPL was flashing a lot of concept pictures and whatnot. We're probably going to be a lot more tight-lipped about our effort. So I apologize, I don't have any CAD models to show you. Next slide. So again, JSC, we've got our flagship project for a long time has been the Robonaut system. Started in about '97, went through Robonaut 1, went through to about 2005, 2006, and then we started the Robonaut 2 project with some outside investment from General Motors. We recently flew that robot to the International Space Station, so we have a pretty long history of dealing with high-dimensional systems in remote areas suffering from really terrible communication and large latency. So we feel pretty good about tackling that side of this challenge. The networks on the space station are not very good, and we have to deal with that all the time through our task development. We also, we have pretty rugged systems. This was a recent robot we developed on the right-hand side, Centaur 2. It was an extension from our Centaur 1 platform. Our theme is we get our robots out in the field and we use them and we fly them. So, but like I said, JSC is really responsible for all the project management, test facilities, labs, the bulk of the system engineering and integration. We are leading that component of it, and we're doing all of that in assembly. So, next slide. Our university partners that we've brought in for this is where we're really getting kind of the ultra specialized skills. JSC hasn't had a whole lot of need for example, bipedal locomotion, although we have had some, we've got our sights set on some interplanetary missions in the future. But reduced gravity or varied gravity bipedal locomotion has been somewhat of a focus, albeit not a strong one. So Texas A&M, we're working with Professor Aaron Ames there to help us develop algorithms for bipedal locomotion. Next slide. Reducing that high-dimensional system down to a task environment. We're going to be using the whole body control framework from Luis sent us at the University of Texas. Next slide. Like I mentioned before, we've been developing an exoskeleton. We just did a press release on it. It's the middle picture. So we kind of springboarded from IHMC's earlier EXO and integrated a lot of Robonaut technology into it. And so they're going to be helping us with some of the new actuation that we've designed for that EXO and pulling it into our robot. Next slide. We're actually working with iWalk as well. They know a lot about locomotion, especially bipedal energetics, and so we're going to be leveraging a lot of their know-how with our system design. Next slide. And we're also working with Professor Rob Platt from SUNY. Actually came out of our lab and then became a professor at SUNY. So actually was the controls lead on our R2 development. So there's a lot about manipulation and planning. Next slide. Purdue, we've been working with Purdue University for a while on electric motor research, and we're going to be incorporating a lot of the new types of motors we've been developing into this robot. And so I'm a huge believer in electric machines and the promise that they hold, especially atypical types of them. Next slide. We're the component we're working with Lockheed. They have a lot of advanced aerospace materials. The weight's going to be the mass of this robot, and therefore the inertia of the robot's going to be incredibly important. And so we're going to be incorporating a lot of advanced aerospace type materials into the structure. They're also going to be doing a lot of structural optimization for us. We are taking mass and therefore system weight incredibly serious for this competition. And they're also going to be providing some fabrication capabilities for us, a lot of additive manufacturing. Next slide. Oceaneering Space Systems is a large contractor in our lab. They have a lot of system design and robot engineering experience. Anything from the 600-pound spider we developed, Centaur 1 in the middle, and then pair of legs, 7 DOF legs on the right-hand side that we're actually flying up to attach to Robonaut 2 on the space station in July on the SpaceX flight. And so those are being tested in our active gravity off-road facility at JSC. This robot's going to be clothed. We like to put clothes on our robots. And so soft goods is a big component of it. This robot's going to fall down a lot. And we believe in fall protection and pretty novel ways of dealing with soft goods for fall protection. And Oceaneering will be handling that as well. Next slide. Jacobs, another general contractor in our lab. They just going to be providing a lot of general mechanical and electrical expertise. Next slide. And that's it. So, sorry there wasn't too much there.
Okay, my name is Stefan Schaal and I'm presenting the effort which is led by Raytheon Missile Systems together with Raytheon Sarkos and the University of Southern California. And so the idea essentially is that Raytheon Missile Systems is the coordination of our team. Sarkos is really going to build the robot, and then DRC will work on control and perception of this robot. Next slide, please. So this is the concept of the robot which we're thinking about, and just a little bit of history. Sarkos, now it's called Raytheon Sarkos, has been working on hydraulic robots for more than 20 years. So they had originally in the early 90s hydraulic robots arms which were extremely high performance. And I still have 2 of those in my lab actually, and they still work after 20 years, no problems at all. They developed, I think, some of the humanoid robots that you find at the Disney parks. They developed some of the first hydraulic humanoid robots, which we had in a collaborative project with Chris Atkinson and the ATR labs in Japan at the late 90s. And they also developed 4 humanoid hydraulic robots, which are currently, 2 of them are in Japan, 1 of them is at CMU, and 1 of them is at USC. So one of the interesting components which we have as a team, actually, we have a humanoid robot, a hydraulic humanoid robot ready to go, which has a lot of similarity in its control and design elements, in its communications, as this robot, which is going to be developed for the robotics challenge. And so they will actually allow us to work with a robot from day 1 onwards. We will not wait for 9 months. We will work with a hydraulic robot from day 1 onwards and work towards these tasks. This robot which we have is not quite capable of doing all the challenge tasks, but it has a lot of similar capabilities. Now, the robot which is going to be developed, it was the top one. It's shown here in a sketch. And essentially it's going to be a humanoid robot. It has 7 degree of freedom arms. It has a 3 degree of freedom hand. The hand design is still under debate. We can have various designs. I think Sarkos has 3 designs already ready to go, and we'll find out which one we need. Do we need to be able to fall over or not, for instance, how rugged the design has to be. We have a perception head, potentially with a 3 degree of freedom neck, can be a fewer degrees of freedom, we don't know yet quite. We can actually have more sensors on there and fewer degrees of freedom, or fewer sensors and more degrees of freedom. We don't quite know how to trade that off right now. We envision to have definitely laser rangefinders, we envision to have Kinect-like sensors, and we envision to have regular vision sensors like Bumblebee stereo vision systems. The legs will have 6 degrees of freedom as we anticipate, and they will be very lightweight. So some of the degrees of freedom may actually be passive. We don't know quite exactly how it's going to work out. And the robot will be covered in rugged shells. It is supposed to be able to fall over. We really care about that. Since it will fall over, there's nothing we can do about that. It's a challenge. Let me go, next slide please. A little bit more into the details about how this will be controlled, the system. The robot is supposed to be lighter than 165 pounds. To be honest, it's supposed to be much lighter than 165 pounds. The hope is to get towards 100 pounds or something like that. And that will allow the robot to pretty much take everything on board, computing and power supplies. So it's supposed to be completely untethered. It's ambitious, and we don't quite know whether it's going to work out, but we really want to go for that. And if it goes in the 100-pound category, we should be able to do that at least for some decent battery lifetime. Now, the control architecture, in essence, will be very similar with many other people. There will be some supervisory unit, which then basically communicates through wireless to the robot. And if everything is on the robot, then there will be control boards on the robot which control the robot directly. There will be perception on the robot directly. The robot obviously interacts with the real world, and we get feedback to our control or the supervisory unit. We will visualize in simulations and appropriate tools what is going on. The important part will be to deal with the bottleneck of communication. And I will show you this on the last slide. Laurent Eti, who's at USC, who does the perception part, has been working on visual attention algorithms for a long time. So he knows actually how to do selective data transfer, very selective. We will actually work with these abilities to basically bring the most important data over to the supervisor whenever necessary. And if you need more information, well, we have to wait a little bit longer, and the system will sample and basically provide more data. And that's the idea how we think we can cope with the information bottleneck. Let me show you a little bit more about the control areas. Next slide, please. So what is important is Sakura's robots, and here you see actually one of the humanoid robots. Now, yeah, you can play that. Not all of them. Well, let's play them all. This is actually not my work. This is work by Sang-Ho Yon from the APR labs, working with some of our software, and working with one of the Sakura's humanoids, and actually showing some very nice dexterous control and dexterous balancing behaviors. Up there you see some work of our contribution to the learning locomotion program, which created a lot of technology which we're going to use for walking over rough terrain and doing balance control. So you see this kind of the end performance of this robot dog, which was called Little Dog, which basically learned how to do a large number of different behaviors that were pretty complicated terrains. What was behind Little Dog was actually a planning algorithm which basically remembers footholds and then scores these footholds and tries to use only good footholds when it gets in a similar situation. Now, this kind of an approach is actually very suitable to what we're going to do with the robotics challenge, just that the perceptual modes will be slightly different, but we will basically get 3D information of the terrain, discover footholds, score the footholds, and basically find our planning and foothold selection through that terrain. Control, I started that before. The robots of Sarkos have always been torque control robots, which is in the world of humanoid robots fairly rare. Most robots are position control. And the behavior you saw before down here, this kind of fluent, compliant behavior, is due to this torque control modes. And this is something we want to use a lot. Actually, even the Little Dog robot has force control components, which allows it to actually recover from perturbation. So here you see actually the robot goes over completely unperceived terrain, and that is only possible due to some force control mechanisms and model-based control mechanisms. Okay, could I get the next slide, please? And you could play both movies right away. From a manipulation point of view, we will actually leverage a fair amount of work from the DARPA ARM project that we're also part of. And you see here basically what came out of phase 1 of this project. This is the robot currently only with one arm, and by now it has gotten a second arm. And you see it's going to manipulate a whole bunch of different tools. In the lower video, you will actually see that the robot can also operate quite nicely if perception is deteriorating. This is actually showing you what happens if the robot did not perceive the object to be manipulated precisely, but is off. And using tactile perception and some nice feedback mechanisms, actually, you can recover, even if your perception is 10 centimeters off, quite nicely. So these kind of behaviors or abilities will naturally flow into our Guardian humanoid robot for the Grand Challenge. And we don't believe there will be so much adaptation necessary for that robot to get there. Could I get the last slide, please? So I just want to mention perception for one moment. As I mentioned, Laurent IT has been working on this for a long time. And the key component will be to use, I wouldn't want to say standard, but a lot of the standard perception algorithms from mapping SLAM to context awareness, to object recognition, to object tracking, to do this all on board. But given that we all know that perception is really hard, particularly in an outdoors environment, then feeding back selectively with attention mechanisms information back to the supervisor, such that the supervisor can really help and direct either the attention to new points or the robot to move to particular points, or to give the robot direct input about how to plan and where to go next, depending on how lost the robot is going to be in the particular scenario. And we will basically develop control interfaces which will be able to do that, which basically display the entire robot and then selectively more and more information about the world as it gets available, such that the robot can be helped if it's needed. Otherwise, it will go autonomously as far as it can. All right, so that's all. Thank you.
Hello everyone. I am Narito Suzuki from Team Shaft from Japan. We have great honor to be here in so meaningful program's kickoff event and to tell our challenge to you all. Next, please. First of all, we very want to express our appreciation on sincere contribution from all over the world to relive Japanese disaster on March 11, 2011. With a lot of support from all over the world, we have promoted our reconstruction step by step. And we think this Java Robotics Challenge is so thankful and meaningful project to challenge such a big program like Oceaneering. We built Team Shaft from Japan to contribute future disaster relief. And we also have great honor to be selected such a great opportunity. Our supporters and our team trusted on a great potential of humanoid for a long time. And we think this is a good opportunity to contribute to accumulate the technology which is used in the disaster relief situation, not only Japan, but also all over the world. Next, please. And we built Shaft Inc. to have a prime contract for this program. Shaft Inc. is a spin-out company which is born in May 15th of this year from the robotics laboratory of University of Tokyo. Then I will introduce the three key technology from the robotics laboratory where we graduated. First, high-power hardware technology. Second, high stability on bike walking. And third, many experiments to achieve humanoid behaviors in real world. So I will show these technologies one by one in detail. First strength of our technology is high power hardware. Probably you might think the power of humanoid is very important. And with the real power, humanoids can work stably and can do tasks stably. But nowadays, ordinary electrical licensed humanoids can generate 1/10 power as humans. But with our technologies, it can generate 10 times as current, and so it's same as human can do. This video shows, our first video was, this video is about jumping, and our robot can jump itself. Its weight is 50 kilograms, but it can jump and lift itself. Maybe you saw the robot lift dumbbell of 62.5 kilograms, and it can throw an apple to the head of 500 millimeters. Next, please. To achieve these high power humanoids, it need to accumulate technology on how to drive motors, not just motor itself. So we mean motor driving system is one of key of this power. So high power motor driving mode and water cooling motor systems. Our technology, one of characteristic of our technology is using electrical submotors. And with these technologies, our system can generate 10 times of current with same size motor and same power, same regulated power models. Next, please. Then I'll introduce the next strength of our technology. This is high stability on bike walking. Look this video. This robot doesn't fall if it's kicked. There are two secrets of this technology. One is very strong, robot very strong. So what I told before, and with the big power of this robot, the robot can move their legs so quickly to the stable point. Furthermore, the systems can calculate so quickly on the footstep planning. And with footstep planning, the robot can find the most stable point, and the robot can move their legs so quickly with the powers. Next, please. The third strength is about many experiments to achieve humanoid behaviors in the world by life-size humans. Our graduate laboratories have achieved a lot of tasks for the 20 years, and with use with robot language and robot development system. These systems, the characteristic of this system is the first is based on Lisp language. It is very useful to rapid prototyping and to write intelligent software. And the second characteristic of this development system is it has a lot of library which is very useful to robot experiment, like 3D model processing, kinematics, dynamics, and a lot of algorithms from AI research. It is also integrated with ROS system, and we can use these components to experiment our robot experiment. Next, please. Please look at this video. So driving wheelchair, towing heavy object, using tools and opening the door, picking up object on the ground and grabbing apparatus. So it is through riding apparatus and it can carry heavy object in theory. So these selected movies, which is very related to the DARPA Robotics Challenge 8 event. Our laboratory, our graduate laboratory, experienced a lot of doing task experiment with the such a development system, which I told. Next, please. So, thus I introduced 3 key technologies from our graduate laboratory. We Team Shaft integrated this technology into one life-size and practical use humanoid, which can be used in disaster response situation. Next, please. This is our schedule. Firstly, this is our schedule, and we plan to evolve our humanoid hardware in 3 times. And we will make first we will make each component like control, manipulation, perception, user interface. Next, we will integrate into one life-size humanoid. Next, please. So finally, we appreciate program managers and all contributors who promote this program and for giving us this chance to contribute to the accelerated technology. And we would like to contribute through open source activities with sincere acknowledgement to our big supporters. Without our big supporters' support, we could not stand such a start point. With a lot of support and a lot of expectation, we will make a good human which can be used in the disaster response situation. Thank you very much.
Hello, my name is Dennis Hong. I'm the director of Romella, the Robotics and Mechanisms Laboratory at Virginia Tech, and we are Team 4, Tactical Hazardous Operations Robot. So for the DARPA Royce Grand Challenge, we have a unique approach. We're actually proposing to develop 2 different humanoid platforms with very different approaches. The first robot is called Thor. It's based on one of the cutting-edge research, the new class of actuators called series elastic actuators. It's based on the new type of actuator that we developed through another project sponsored by the Office of Naval Research for firefighting humanoid robots. We'll talk about them in the next slide. The other one is called Thor OP. Thor OP is, if I might say, it's based on the more traditional humanoid robot design architecture using high gain position controlled servos using ZMP-based control. It's It's based on one of our very successful full-size humanoid called Charlie. Our team is composed of 4 organizations: Virginia Tech and University of Pennsylvania, led by Professor Dan Lee, Harris Corporation, and also Robotics Corporation. Together we have a lot of experience in humanoid design, autonomy, and manipulation. So the first robot that you see over here, this robot is called ASH, Autonomous Shipboard Humanoid, under the project Sapphire Shipboard Autonomous Firefighting Robot, sponsored by the Navy. So for this one, you can see these new type of series elastic actuators that has a compliant membrane that use low hysteresis tightening springs with inline load cells for force control and position control, and currently it's working very well. So Thor is going to be based on Sapphire. The one that you over see is Charlie. It's a 1.5 meter tall humanoid robot that we use for drone research and micro information and autonomous behavior. We also use this robot for coverage for Global Cup. Most of you know Global Cup is an international autonomous robot soccer competition with the offshore goal by the year 2050 as robots play soccer with including World Cup champions. Partnering together with University of Pennsylvania, our World Cup team is the world champions of both sides, so we're Charlie, and also we're the world champions of the big side with another team company robot is called Darn OP, and we're the world champions last year and this year as well. We have other competition experience as well. For the 2007 DARPA Urban Challenge, Virginia Tech had a team. Victor Tango was a co-team leader, he placed 3rd place, and Dan Lee's team from University of Pennsylvania placed 5th place. Magic 2010 was another big competition for multiple autonomous robot competitions. We qualified for it. UPenn was the 2nd place winner, and Red Hawk haptic system is a new type of haptic system that Harris developed that we're trying to use for this competition. So I already talked about Virginia Tech's expertise in humanoid design and development. We still believe that Charlie is the first and probably the only full-size, fully autonomous big-size humanoid robot in the United States. And we have other humanoid robots development and experience with other vehicles. Again, UPenn is renowned for their work in perception, autonomy, and path planning. Harris has more than 20 years of experience in working with the government for manipulation tasks and teleoperations over degraded communications. And Robot is probably familiar with these the robotic actuators, dynamics motors. So Robot is coming up through this project. We're announcing a brand new line called the Dynamics Pros, which are the industrial strength servos that uses not harmonic drives, but we're using some very interesting new type of gear reduction is called cycloidal gears, and we'll be using these actuators for some of our robot jobs. So this is the first platform, the Robot 4. So as you can see, we have some novel features. Oh, by the way, this picture is the picture from Sapphire, sponsored by the Navy. We have these Pearl actuating schemes, which has very good properties for these type of robots. And as I mentioned, in the past 30, 40 years with roboticists, we try to get rid of compliance or springiness because we want to have precise solution for manipulation and for manufacturing tasks. But now we scientists and engineers understand the importance of springiness, so compliance for walking especially, and also for robots to work with humans for safety. So the new class of actuators is called series elastic actuators, and we intentionally put springiness into it, and we're trying to control not just the position, but also the force. So that's what we're trying to do. We also developed this new type of tiny, small controller that does that in 10 kilohertz control loop, which was very, very successful. So we're going to be using all of those technologies for Thor. Now the difference between Thor lower body and the current robot Ash is that the robot Thor is going to have a full range of motion for all of the turns, just like a human, so it can walk with full legs, can sit down, and also stand up and fall. Also, we'll be running it untethered using a battery. Currently, we expect it's going to run for 30 minutes, but we're going to work on that to increase our program. The other robot called Thor OP, OP stands for Open Platform. It's a different approach. This is, as I mentioned, more based on the traditional architecture of using high gain position control servos and using ZMP-based walking. And this is based on, so you can think of it as a souped up Charlie. So this will be done rather easily, I should say. But the cool thing about Thor OP is that we'll make this fully open source software and open source hardware. Probably you're familiar with the Darn OP robot, sponsored by the National Science Foundation. It's a small humanoid robot that we made it for research and education. And we made it open source, and it has a huge impact. Currently, about 400 units are being used worldwide in less than 1 year. So we believe that after this competition, once we release Thor OP, it's going to have equal or more impact, positive impact for the robotics community. And for the Thor OP, we're going to be using those dynamical Thor actuators for Thor OP. For software, we've been working very hard developing different type of disturbance or rejection algorithms using machine learning technologies. And we already demonstrated all these capabilities with our smaller scale robot, Darn OP, for rough terrain handling, disturbance rejections of the disturbance. It can use its ankle torque and then its hip or its arm to balance it, walking with 4 legs, and even if you give a different payload, even though the load changes, it knows how to balance itself. So we're trying to port all of these to our larger robots, Thor and Thor OP. Of course, as we talked about it, in a real disaster site, communication is unreliable. Bandwidth in communication gets caught, so you cannot just do regular teleoperation. With the expertise from Harris, we're going to do model predictive teleoperation, so it works over degraded communication links, and you have some nifty graphical user interfaces with these haptic feedback for controlling, for the operators to control the robot. So that is Team Thor. This competition, I believe it's the craziest, the boldest, the most expensive probably, but the most challenging, yet I believe it's the most important robotics project ever in humankind history, I think. I mean, this is our mission. If you think about it, the technology that we will be developing through this project, whether successful or not, in the future, if we can even save just one person's life, then everything is worth it. I mean, together we're really trying to change the world, and that's what we're trying to do. So thank you, we're Team Thor. Thanks.
All right, thank you everybody from all those wonderful TrackA teams. We're going to take a break right now. I want you all back here at 3:30 on the dot, and then we will hear from the TrackB teams. Thank you.